Well, in response to so many questions that we've received in recent times, we thought it would be useful to try to put together a basic primer on prophecy. Many people, for the first time in their lives, are asking serious questions. Where in the Bible does it say this or that? And what's coming? Are we in the end times? And what about America? And so forth. Very basic questions. And so we thought it would be useful to try to cover these materials from a ground floor, from scratch, and we'll try not to jump into too much Bibleese or jargon that tends to puncture our conversation so frequently. We're going to do this in 4 sessions. This first session, of course, is the introduction. And we're going to deal with 2 issues. We're going to try to talk about the nature of prophecy. What are we dealing with when we talk prophecy? And secondly, how sure can we be? Aren't there theories and ideas like this throughout the ages? Hasn't everyone always felt that they were approaching the end times? Where do we come off being so certain that we're approaching an important period of time? So that's the first session. The first thing we're going to talk about is the nature of time. We take time for granted. It all goes back to some basic fundamentals that most of us may not have thought much about. Let me take you back to high school geometry or trigonometry. If we have a triangle and we add up the angles in that triangle, it adds up to how much? 180 degrees, right on. And no matter what kind of a triangle we draft, if we add up the angles, it always adds up to 180 degrees. How many of you learned that rule in school? Sure, okay. Well, suppose we go out together in a large field nearby with a transit, and we lay out a very large triangle, and we add up the angles of that triangle, and it adds up to more than 180 degrees. What would you conclude? That Chuck screwed up again, huh? No, what we've encountered is the curvature of the earth. You see, this little rule that we all learned in school is only true for a universe of 2 dimensions. That's why it's called plane trigonometry or plane geometry. And if you have more than 180 degrees, it implies that you've encountered a convex curvature. In fact, if you take a course in spherical navigation, or in navigation, you'll include in that course some spherical trigonometry in which you can have a triangle with 90 degrees in each corner because it's in a 3rd dimension. Now, if you have a triangle with less than 180 degrees, you're in a hyperbolic paraboloid, but I don't think that's ever concerned any of us here, so I'll just move on, but I throw that in for those of you that are mathematically oriented. This is the kind of insight that caused Dr. Albert Einstein, as he was grappling with the nature of space and time itself, to come up with a special theory of relativity in 1905, in which he realized that length, mass, and velocity and time are relative to the observers measuring them. But he generalized that in 1915 to the general theory of relativity. And what's important about that to us here is that it resolves the fact that there's no distinction between time and space. In fact, a physicist will always speak of space-time. You and I speak of space and time separately, but the general theory of relativity ties them together. In fact, Einstein recognized that we live in not 3 but 4 dimensions. And this is no longer just a theory, it's been confirmed over 14 ways to better than 19 decimals. It's today a basic insight of science. One of the things we want to understand is that time can change. Let me give you an example. It's a very graphic example. There are atomic clocks. These are clocks that are extremely precise. There's an atomic clock located at the National Institute of Standards and Technology in Boulder, Colorado. There's an identical clock, virtually identical clock, at the Royal Observatory in Greenwich, England. And these devices are accurate to better than 1 second in a million years. In fact, the recent one installed in Boulder is accurate to better than 1 second in 20 million years. And these are all based on the natural resonance of the cesium atom, which can be exploited to render incredibly precise time standards. But the reason I bring this up is the one in Boulder at NIST, it ticks 5 microseconds per year faster than an identical clock at Greenwich. Which one is correct? They both are. These are extremely precise clocks, and yet they differ 5 millionths of a second per year. Why? Because the one at Boulder, Colorado is at 5,400 feet above sea level, and the one at Greenwich, England is only 80 feet above sea level. You see, if you take an atomic clock and raise it by 1 meter, it speeds up by 1 part in 10 to the 16th. Not enough to change your personal schedules, but it's predictable and measurable. Time changes with a difference in gravity, among other things. Now, there are other demonstrations. They actually took atomic clocks like this and put it on an airplane going around the world eastward. And it lost 0.059 microseconds compared to one at rest at the observatory. They sent one around the world westward, and it gained 0.273 microseconds. And I won't go through the reasons. By the time you account for all the motions and differences, that's exactly what the theories predicted. That's exactly what was measured. But perhaps the most provocative example, which you'll read about if you study a textbook in this area, is the example that's usually cited of 2 hypothetical astronauts. These are 2 imaginary astronauts that are born at the same instant, and we're going to send one of them to the nearest star. Now, if we look at the night sky, the stars all look different brightnesses, but they're all actually at different distances. But the one that's closest to the Earth is a star called Alpha Centauri. It's the 3rd brightest in the heavens. And from the Earth to Alpha Centauri is about 4.5 light years distance. In astronomy, we measure distances by the distance that light will travel in a year. And Alpha Centauri is essentially 4.5 light years away from the Earth. Now, if we send our theoretical astronaut to Alpha Centauri and back at half the speed of light, let's assume we could do that, then it would take him 9 years to get there and 9 years back. You follow me so far? The question is, that's Earth time, where we are. What does his clock read as he makes this trip? Well, that's calculated by what's called the Lorentz transformations, and the time in the spaceship will be in these 18 years on the Earth. His clock will only read 15 years and 7 months. In other words, he will be more than 2 years and 5 months younger than his twin brother. Now, if that doesn't bother you, you weren't listening carefully, okay? See, time for him is different than time for us on the Earth because by nature of his velocity and so forth. To dramatize this, let me indulge in the fiction that we could send him at 99.99% of the speed of light. I'm not suggesting we could do that. There's some other problems, but let's assume we could. And that would take then 9 years for him to make the round trip on our calendar. But on his clock, it would be only 33 days. You see, his time is different than ours. I think it was Dr. Gerald Schroeder, who's a world-class nuclear physicist, participated in 6 of the atomic bomb blasts. He makes his headquarters in Jerusalem. He's a good friend. He's the one that's pointed out in some of his writings that if you take the expansion of the universe as roughly 10 to the 12th, and you take the age of the universe, it appears to be about 15 billion years old, but that's at the fringe of the universe. If you measure that in Earth time, it would be, guess what, 6 days. Same expansion factor. But let's move on. The key point for us tonight is to recognize that time is not uniform. Time is a physical property. That's what these changes teach us. See, time itself varies with mass, acceleration, and gravity, among other things. You and I exist in more than 3 dimensions. In fact, we actually, apparently, exist in about 10 dimensions. Back in 1854, in June of 1854, Georges Riemann gave the most important scientific lecture that's ever been given, where he introduced the concept of metric tensors. That provided the mathematics, which then 60 years later resulted in Einstein's general theory of relativity, because it was Riemann that provided the mathematics for it. And Einstein applied that, recognizing we have 4-dimensional space-time, more than 3 dimensions. That's what we call a hyperspace. A hyperspace is any space within more than 3 dimensions. And Einstein went to his death frustrated because he didn't have the insight to go another dimension. It took Kaluza and Klein back in 1953 to recognize by adding some more dimensions they could resolve light and supergravity issues. It was in 1963 that Yang, Mills, the 2 of them, developed fields that explain electromagnetic and both the nuclear forces, the weak and the strong nuclear forces. The point is, as scientists began to realize that there are more dimensions involved than we're generally aware of, it started to resolve the classic dilemmas in physics. Even as recently as 1984 and following, scientists are now speculating that we actually live, for mathematical reasons, in 10-dimensional. They speak of superstrings and so forth, and that we live in 10 dimensions. I mention this because I think it's really interesting to discover that 800 years ago, in the 12th century, we had Nachmanides, who was a Hebrew sage, in his study of Genesis chapter 1, came to the conclusion that the reality consists of 10 dimensions. 4 are directly knowable, and 6 are not knowable in his terms. What makes that interesting is this ancient Hebrew sage, studying Genesis 1, came to the same conclusions that our particle physicists today have concluded, that we live in 10 dimensions. 4 are directly measurable, 3 spatial dimensions, length, width, and height, and time. 6 of them are curled, to use mathematical terms, are curled in less than 10 to the minus 33 centimeters, and therefore they're just inferable by indirect means. Now, this whole idea of the 10-dimensional universe is suggestive, because the original creation, of course, is described in Genesis chapter 1, verse 1. But we have sin introduced, and we have the curse pronounced. And some speculate that that's when the creation was fractured, that we are left with 4 dimensions we can directly sense: length, width, height, and time, 3 spatial dimensions and time, and 6 hyperdimensions. We call these 4 dimensions that we can sense the physical dimensions. And the ones that may be hyperdimensional may embrace what we generally defer by calling the spiritual dimensions. But there is a reality larger than our physical dimensions. We now know that. But that's what we're going to start moving into as we start talking about prophecy. See, the other misconceptions, the part we want to do when we get into this kind of a subject is to set aside baggage, misconceptions, presumptions that are inaccurate, that we all have. Most of us assume that time is linear. We assume that tomorrow will be like yesterday, next week like last week, next month like last week. We think that time is linear, intrinsically. And when we were in school, the teacher put a line on the blackboard from left to right. The left end would be the beginning of something, the birth of a famous person or the founding of an empire or what have you. The right end of the line might be the end of that person or the empire, what have you. How many of you made timelines in school? Can I see a show of hands? Sure, we all have. And so because of that, we jump to some conclusions. Incidentally, this dimension we call time is a strange dimension because we can only move in one direction. You see, we can only move forward and we can look back. What we can't do is move back and look forward. Whenever I often, in an audience like this, I'll ask, how many of you remember tomorrow? When I give that talk in California, I hesitate because I'm sure I'll get a hand or two, but anyway. See, we move forward in time and we can look back in terms of history. But we can't move back. It's a popular theme in fictional literature to go back in time. It's a very colorful instrument of writers. But it leads to paradoxes, because if you can go back in time, you could kill your grandfather, and then that starts to lead to some problems. So, and you can play around with those ideas as just mind stretchers, but the idea of moving back in time is generally rejected by most serious thinkers. But the other side of this is what we're going to try to do. We're going to indulge in the opportunity to look forward. But I want to show you why that would require a supernatural insight, and that's exactly the point we're going to make. And so there's another concept we need to set aside, and that's the concept of eternity. Because we think of time as linear, when we encounter the concept in church or wherever of eternity, we tend to assume that that's like a line that starts at infinity on the left and goes to infinity on the right. We tend to visualize God as someone who has lots of time. That's very poetic. It's very colorful. It shows up in our hymns, in Amazing Grace, what is the 4th stanza, when we've been there 10,000 years and so forth. We tend to imagine eternity as simply having lots of time. That's fine, but it happens to be, the idea that God is somebody that has lots of time is very poetic, but it's bad physics. What do I mean by that? Is God subject to the restrictions of mass? Hardly. Or acceleration? Or gravity? Of course not. God is not someone with lots of time. He is outside the restrictions of time itself. And this uniqueness of God is his personal imprint. It's like his signature. It's an attribute that he exploits to authenticate his messages. That's what Isaiah alludes to in Isaiah 57, verse 15. He says, "Thus saith the high and the lofty one that inhabiteth eternity."